for that introduction. So that probably sets the stage nicely for everyone to sort of have a rough idea of my background. If you sort of join into the chat between Martin and myself, and then you heard that we talk about some of the things that we did during the pandemic period, especially at the beginning when my lab's completely shut down. So I'll show you some of that today. Now, when Sammy asked me to sort of give a talk during this series, and I talked about it a little bit, and actually I'm not going to overburden you with a lot of chemistry or even material science, and I try to take a slightly different tack. So to me, you guys are the next generations of people who will do machine learning application to chemical science or physical sciences in general. I think I like to focus on the principle and the concept behind it rather than the technical aspect of the machine learning or even the chemistry that I discussed. So we will probably spend more time talking about that sort of thing. So with that sort of explained the title that I went with, the machine learning with causality in chemistry. Yep. So I'd like to start with this slide. Now, this information was taken from a sort of survey that was done about 2 years ago by the ACS. And the questions that people were asked in chemistry was, do you think machine learning is overhyped? Now, hopefully you will see that almost half the people in chemistry being asked either agree or strongly agree that machine learning is overhyped. And this is a breakdown of the research areas that people actually work in for those 151 responses. So we have a trust problem, at least in chemistry, that a lot of practitioners do not trust machine learning's technique or outcomes. And the reason for that is because there are various things that can go wrong when you start applying machine learning to chemical problems. So there is cognitive bias, there's experimental bias in the data you're going to get. And then there's the problem of spurious correlation and interpretability. And interpretability is going to come up again and again in physical science when you talk about machine learning, because in order for someone without any experience in machine learning to trust the predictions or the models built by machine learning, you need to convince them with interpretability, not the prediction power, because they will never be convinced with just simple correlations. You need to show the causal relationship. And that's one thing I want to talk about today. All right, so now I prepared the talk, and then just about a month ago, some people in I think the Rosalind Franklin Institute and a lot of other practitioners in the UK and in the US prepared this paper that they published in Nature Chemistry. And they more or less did at least half the job for me. So that made my job today really simple. I strongly recommend you all to read this paper. It's an opinion piece, but it laid out the basic best practice of using machine learning in chemistry. And once this is set down in writing like this, it's extremely important for we all to sign up the concept, and they are sensible concept. So in that paper, there is an important table which I listed here for a checklist of reporting and evaluating machine learning models. So you got data sources, either data source publicly available, is there any potential biases in the data set? So first rules of anything computational, rubbish in, rubbish out. If your data is biased, your prediction is biased. So the first thing we must do before we even attempt machine learning is check to see whether data is biased. If it is biased and you can't do anything about it, at least know that it's biased. So it's going to affect your conclusions. Data cleaning is quite frequently done, but not always properly explained. So in this sort of checklist, the most important statement there is actually are all the data cleaning steps clearly and fully described. Now, what we do not want is a paper describing excellent predictions or models, and then nobody can repeat it because they can't reproduce that training set. They don't know how the data is cleaned. They have no idea whether they should trust this paper or not. And more often these days, if you publish something like that, most of the journals kind of return it. The standard in publishing machine learning publication is getting into shape now. So reviewers and editors are a lot more strict on this thing. Now, then we move on to data presentations, the comparisons against standard feature sets provided. So if you use a different data set from other people, other publications, and then you get a different results, you really need to do that benchmarking and compare at least the same data set with different models or the same model with different data sets. So you actually have a way to compare between models in different publications. If you publish something based on a set of data that is entirely different from someone else's, then you can't really compare the results between different publications. You don't know which one is the better model. Now, some people might like that, but obviously in the interest of the whole field, that's not acceptable. And then we got 3 more points. Now, model choice, most important thing here is baseline comparison to the most simple trivial models, and then baseline comparison to state-of-the-art models. Again, not something you very often see in publications so far, but this is something we really need to push forward. If you publish a model, it needs to be benchmarked against basically trivial models and the state-of-the-art, so people know exactly where things are. It's not about the most accurate predictions, it's about how to progress our model building as a whole field. Model training validations, these many times you don't see people do, although this is the accurate practice. You need a training set, you need a validation set for hyperparameter optimizations, but then you need a test set that is completely separate from the training validation. It's very often that people sort of combine the validation and the test set into one set because they don't have a lot of data. If you don't have a lot of data, that might be acceptable, but you need to state that very clearly why you did that. But generally, you need 3 sets, not 2. And then finally, all of your code need to be in a public repository because this guarantees the reproducibility of the models. If we can achieve all of these things, then at least people would start trusting the results that we publish. So these are excellent. And as I said, they save me a lot of time. But I want to bring up the last point. The last point we have on machine learning in physical science in general is correlation versus causations. So this is my students' favorite example. If you look at the divorce rate in men, it correlates really strongly with the consumption of margarine. When one goes down, the other one goes down over the year. When one comes up, the other one comes up. But is there a causation relationship between the divorce rate and the consumption of margarine? And on the surface, no, it just makes absolutely no sense whatsoever that there's a causal relationship between them. So this is typically what we say spurious correlation. And there's a whole website dedicated to this down here. If you want to look up more spurious correlation, you can go there. Things like ice cream scale sales and skin cancer, that sort of thing are also in that criteria. So they're not causal relationship, but they're related. They're just not causal. So since we've been having the pandemic, I like to use a topical example. So here's a study from Warwick last year, and it is probably one of the rare studies that is a very good examples of how to establish causal relationship. So in this study, they look up to the relationship between the eat out to have out scheme and the infection rate during that period, and they establish that it is actually a causal relationship. So to do that, this is just one part of the data that is presented. But on the right-hand side there, you got the infection rate during certain periods. So we got 3 periods here. Now, when there's significant rainfall on the eat out to have out days, you got a decrease in the infection rate. On the same day, so the third row, on those same day, but without rainfall during the lunch and dinner hours, you do not see a drop in the infection rate. On a non-eat out to have out day, if there's a rain during lunch or dinner time, again, you see a drop in the infection rate. So there's a clear correlation between these two, and And it's the kind of correlation that you can put a pin on and say there's a causal relationship there. It's clearly linked together, and you can benchmark it against the sort of two negative scenarios there, so that you know that you can trust the relationship between the rainfall during lunch and dinner time of the 8-hour day and the infection rate. So this is one way of establishing causal relationship based on the first level correlations. So how does that work in the real context of chemistry? I'm going to talk through one example today. Actually, I'm going to talk to two, but I've spent most of my time in the first example. So one of our interests is solubility predictions. Just to show you how important it is, this is the first solubility challenge in 2008. And then the same people published a second solubility challenge in 2019. So 11 years after the first one, because no one managed to solve the first one. And solubility obviously is extremely important. These two publications with the challenges here still remaining unsolved, unaddressed at the moment, just highlight the need of the whole field to have a reliable solubility predictions model for these compounds. Now, why is important? The aqueous solubility is an important property for any drug design. In any drug candidates, you need to predict the aqueous solubility because it's linked with bioavailability. If the API is extremely active, but the solubility is too poor, you're going to have to do something about it to improve the solubility. Otherwise, you can't get into bloodstream, you can't deliver it into the right cells in the patient's body. But also solubility in organic solvent is kind of important as well, because if you think about all of your workup and purification of most of your reactions, an extraction is in there somewhere. If you do organic reactions, the most common activity you're going to do is an extraction. And extraction is entirely based on solubility. So if you know the solubility of your product and your impurity on your byproduct, you can select the solvent to selectively clean out everything else, just keep your product. And that's what we really want in terms of solubility prediction in organic solvents. So prediction in both scenarios are extremely important in chemistry in general, in medicinal chemistry. Prediction in organic solvents are rare because most of the money is spent on the medchem aspect, which is aqueous solubility. So when we came into this, we have a model wish list. Now we didn't jump straight into building a model and try to improve it because we know that it is extremely difficult. Many other people have tried before us. So we took one step back. And what we want is that we want to build a model based on descriptors, which actually represent physical aspect of the dissolution process. We want to be able to rationally improve the model based on understanding of the descriptor and their importance in the model. We know that data is noisy, so we have to set ourselves the limit that we're going to be as accurate as training data. You can never be more accurate than your training data. If you build a model that's more accurate than your training data, then it basically means you just overtrained your model and it's never going to work well outside your training data. We want to be able to reproduce the established physical chemical behavior of solid solution equilibria. So this is a causal term. If we can reproduce established physical chemical behavior for solid solution equilibria, we know that the model actually represents the physical reality of the phenomenon. So we can trust it. And finally, we want to set the standard here. We really need to benchmark against other methods, against realistic targets. So no more it only work inside my training data, and then it work poorly outside my training data. It has to work out well outside the training data. So I'm not going to spend a lot of time going through the chemistry. We use DFT to generate our descriptors. We divide them into solid solutions and solvent descriptor. Solvent is quite simple because within the same solvent is self-consistent. You don't even need it. But we took melting point to represent the solid, and I'll talk about that later. And then a lot of the descriptors actually focus on the solution, which is solvent-solute interactions. So the first order of business is to get that data. It turns out there's not a whole lot of data for organic solvents. So if you mine the reactions database, you end up with about a few hundred data points for organic solvents. Water, you get lots of data, but we limit ourselves just to what we can get from the sort of open access, open source data. So we got about 1,000 data point for water, a few hundreds for HFC organic solvents. Now, hopefully you recognize straight away with this little data, we probably don't want to touch any sort of deep neural network, anything too fancy. We don't have enough data to play with. But what's more important is that the distribution of the log S, which is the log of solubility, looks pretty good. It's spread out evenly enough. Now, what you don't want is something that just got a sharp peak here, because that means your data is biased. Most of predictions going to fall into that range, but we have a reasonably even spread, except for the water data. So in the water data, actually, we made a chop here. We cut it across here so that we don't distort the data too much. But with the organic solvent data, we keep them as is. We got too little, and they seem to be reasonably well distributed. And then it comes to the noise. So it's worked out quite well for us that someone else already done the work and established that the error in literature solubility is log S plus and minus 0.5 to 0.7. Now, this is terrible, because if you think about it, that's on a log scale. On the real term scale, we were talking about something up to about 4 times errors in the values, in the absolute values of the solubility measurement. And it's quite common because you got impurity in the solid, you got impurity in the solvent, and so you got errors in the solubility measurement. And turns out it's that large. So bear that in mind. Once we know that the training data is that noisy, which basically means these x-axis here, the experimental log S, is not all that reliable. Any of these data point can be anywhere between here and here. Yeah. So we need a new metric. The traditional R-squared MSE doesn't take into account the noise in the experimental data. So we added 2 new metrics. Percentage of log S predictions within plus and minus 0.7, so about as accurate as the training data, and percent of log S prediction within plus and minus 1. That's about the range where the prediction is still useful. So 10 times errors in the predictions of the solubility. So hopefully you will see that we got a very narrow zone of operation here. The data is already that noisy, but if the prediction is beyond that, then prediction is not useful. This is exactly why solubility prediction is so difficult in the past. So just to show you here how it works, this is basically the plot between predicted values, experimental values, and these 2 red lines represent a plus and minus 1. So anything within that zone is good, anything outside is bad. All right, so now that we got that, we can look at the descriptor. Now, we started with 22 descriptors, which is very few compared to most of QSAR approach, where people throw hundreds of descriptors into the predictions. The problem is we only got less than 1,000 data points. We don't want hundreds of descriptors, because then we will overtrain our model extremely quickly. Also, the other problem is if we got 100 descriptors, we can't interpret the model anymore. So we want to keep the number of descriptors to as few as possible. So what we do is we plot the correlations between the descriptor. So anything that's in red is strongly correlated. Anything that's in blue is not correlated. So we spot a few that, yeah, we expect them to be correlated. So we remove them. Now, the good news is if you plot the principal component analysis for the whole 22 descriptors, it also says that at about 14 descriptors, you got pretty much 100% of all the variation. So the correlation agree with the PCA. We can cut it down to 14 non-correlated descriptors. This is brilliant for us because these are orthogonal descriptors, which means it's a lot easier to interpret the model. And then it comes to the model optimization. So on the top there is the extra trees models. We basically optimize the number of trees and optimize for MSE, which is the errors in the prediction. And basically up to about 50 to 100, it doesn't improve much anymore. And so obviously the less tree you have, the less the more reliable the model is going to be. And then the same applies to in this plot here. What we have here is a neural network, just a simple neural network. Again, we optimize a number of neurons or nodes in a single hidden layers. And then we decide, well, actually 100 is plenty. We don't want to overload it with more nodes. It just make the model overtrain. So there's small thing like that. But what's important here is we focus on the results. Now, we did have two linear model, and yes, we expect them to perform badly. This is, remember the checklist. We want to have the simplest models so we know the baseline of how bad they can get. The one we're interested in are the non-linear model, and we got them here. R square MSE log S plus or minus 0.7, log S plus or minus 1. Don't pay attention to the number too much. What's important is that the standard deviations for each of these metrics across the non-linear models are actually quite small. Now, some people might say this is bad because you don't know which models are best. I actually thought that this is good because I know that my prediction is not too model dependent. It depends on what I fit into the models, but it doesn't depend too much on the model itself. That gives me a lot more confidence that this is actually physically correct. So here's a correlation between the predictions between different models. You can see right away the linear models predict similarly and they're all wrong. The non-linear models predict similarly to each other. Quite good. So we expect that. And then if we look at the prediction for benzene, for example, this is our best model because the benzene data is the least noisy solubility data you can find. It's a terrible solvent from the sort of health and sustainable point of view. It's a great solvent for solubility measurement. It's clean, it's pure, it's really nicely behaving, and the data is a lot less noisy than anything. So in this case, we got the Gaussian process prediction, which include the error bars. And that's the reason why I'm showing you this. If you include the error bars, everything stay inside the two threshold. If you remove the error bar and just take the predictions, we got about 90% inside plus or minus 1. That's really impressive. But what's really important is this histogram. The error bars values, distributions for the whole lot of prediction here over about 100 compounds, the majority of them is at 0.7. Remember the errors in the training data, 0.5 to 0.7. We are really pushing the envelope here. Most of our prediction is about as accurate as the training data. This is really good. It's not going to get better than this. Ethanols and acetone, we know that it's going to be more noisy because both solvents can be contaminated and acetone is volatile. And so we know that the model will predict a lot worse because the data is far more noisy and it reflects in the prediction. So far so good. Everything seems to make sense. And then one of the things that we did is we evaluate the importance of each descriptor first by taking the descriptor out. So we got 14, we just take out one in turn. And we go through the metrics. So in this case, that's the log S within plus or minus 0.7 and plus or minus 1. And you see that for the ethanol, doesn't matter all that much. So the full set is at the beginning. But for the benzene, if you take out the melting point, the accuracy drops right away. Yep. And then if you use the feature importance plot for the random forest models, in this case, the extra tree, then it does exactly the same thing. It shows you the relative importance of each of the descriptor on the left-hand side is ethanol. So melting point is important, but there are other things important as well. On the right-hand side for benzene, melting point is the only thing you care about. Yep. And the reason why it's like this is because in benzene, you got very little solvation energy. So think about solubility. It's about the balance between solvation energy and breaking up the lattice energy of your solid. In benzene, you got so little solvation energy, so the lattice energy becomes extremely important. And because of that, the melting point of your solid becomes extremely important. So it makes chemical sense, sorry, it makes physical sense. Now, can we check whether that hypothesis is correct? We move to water. We know that in water, our solvation energy is huge. It's larger than ethanol. Solvation energy in water would beat every other solvent. So skipping melting point makes absolutely no difference. And the feature importance plot say melting points is not really important. In fact, we can skip melting point and get the same performance out of the model. This is really good because it means you don't need experimental data for prediction, so you can predict for new compounds in water, not in benzene, but in water, you don't need melting point. You don't need to make the compounds in advance. You can predict solubility straight away. So this make my industrial collaborator extremely happy. So how does that work? Now that we know that the melting point is not important in water, and it suggests that solvation energy is the most important thing, then we go and improve the solvation energy. So before we were using some very cheap solvent models in DFT, we decide we're going to switch on to something a lot better, which is HFSMD solvation model. So if you're not computational chemist, it doesn't mean much to you. Just know this thing probably costs about twice as much computational power and time, but it gives you better predictions. So once we've done that, you can look, just look at S plus or minus 1 between the two methods. We gain about 5% across the board for every method. Yeah. So again, makes chemical sense to us, makes physical sense to us, and we can actually rationally improve the models without having to throw the previous model away by understanding how everything influences the predictions. So once we've done that, this is actually our water solubility prediction plot. It's really good. So we published it last year in Nature Communication. This is the most accurate solubility prediction models in water at that time. I think it still is, but I might be wrong. There might be a new study that beat us. But at the time, we're still the most accurate in the world. And I did say we're going to benchmark against other methods. So here's the AquaSols method from a neural network 2D method. This is EPISU, which is a method used by the EPA. And there is the Cosmo RS method, which is an ab initio method. So for the same compound, our prediction beat everything else. And Cosmo RS actually takes a long time because it's ab initio calculations. If we move on to other solvents, so ethanol, this is ours, this is everyone else. Again, no competition there. And then finally, we want to take a shot at real compounds, not the compound from our training set, because obviously we train it with that data set. We should be good at that. We want to take real compounds. So my student went to AstraZeneca. I don't get to see their compounds, but we did our prediction on their compound. And this is our predictions for their ethanol data. So they don't have benzene data because they obviously don't use benzene anymore. But this is for ethanol solubility. This is the same set of data, but predicted with Cosmo term, the ab initio in-house method. And then this is the prediction in acetone. You must admit that looks pretty good. I'm surprised that they got that good data from acetone. Again, this is the ab initio method. It looks a lot worse. So all of this is published. The data and the codes are there. And we made a web tools that the web app that you can use our prediction method. If you got Gaussian, you can just do your calculation on your compound and upload it to our web tools, and you can get the predictions. So just to recap on that, we basically take the order box. We call our method a causal structure property relationship, mainly to contrast with QSAR, because we do not want to go in without any understanding and use hundreds of descriptors. And we satisfy ourselves that our model actually represents reality to the best of our knowledge. But where do we go from here? Is it just the one-shot wonder that we get lucky with solubility? So here's another thing that we predicted. What I really want to do is to predict solvent-dependent reactivity. And there's one equation and one database in the literature that allowed us to do this, and this is called the Mayer-Paz equations. So this predict the log of the rate constant of a reaction between any nucleophile and electrophile. If you know those nucleophile and electrophile, and you got their nucleophilicity parameter and electrophilicity parameters, you can predict the logarithms of the rate constant. And there is a database of about 1,500 compounds in Mayer's database. Now, sadly, they do not cover all the bases, but it's the only thing we got. Yeah. And so our interest is like this. If we look at a recent synthesis of this drug here, this API here, there's an amide bond formation there. that they very cleverly managed to pull off, because you got two nucleophile, one OH group and one amine group, attacking an acid chloride. Now, in this case, it selectively formed the amine, and the OH was untouched by choosing the correct solvent, which is acetonitrile. In other solvent, you get competitions, you don't get clean reaction, you need protecting group, and everything just take longer and cost more money. But if you pick acetonitrile, the amines would outcompete the OH completely, give you the product, no protecting group, no mess. So that's what we want to be able to predict. Yep. So that's where we are. I'm not going to go into details. I'll just give you a taste of the range of nucleophiles that we cover, and it's pretty much everything under the sun in that database. There are 1,200 nucleophiles in there, and we can do the predictions of nucleophility across 4 different solvents. So DCM, acetonitrile, water, and DMSO. And this is the predicted values plotted against the experimental values. And hopefully you can see that we are pretty darn close to getting everything within the lines that we set for ourselves there. So the threshold there is plus or minus 2 because of the scale of this nucleophility parameter. But we're quite happy with that prediction that we got using our approach. So this is under review in Journal coming from Chemical Information, Informatics and Modeling. And we just gone through one round of reviews, and both the reviewers are very happy with it. So hopefully it'll be published fairly soon. So with that, I'd like to start my talk. Hopefully I show you a few things about causalities and our approach to making sure that our machine learning models actually represent reality. Most of this work is done by Sam Boubier, who's here, who's my PhD student, who just now moved to Nottingham to do his first postdoc, and Yufeng Liu, who's the master student who on the reactivity projects. And John Blacker, David Hose, and Simon Tomasi, and Natalie Fays have been very helpful with their discussion in this project. And I thank you all for your attention.